This is a continuation of our astronomy unit. This lesson is the sun. On March 13th, 1989, a flood of electric particles from the sun reached Earth, causing a magnetic storm. Bright streamers of color filled the sky as far south as Jamaica. The streamers looked similar to what you see here. These are known as the Northern Lights, or Aurora Borealis. But in Quebec, Canada, the storm brought problems. At 2:45 a.m., the entire electric power system collapsed. People woke up with no heat or light. Traffic lights and subways stopped working. How could particles from the sun take out a power system? The magnetic storm caused an electrical charge throughout the power lines. Electric stations couldn't handle the extra electricity, and they blew out, taking the power system with them. So what is the structure of the sun? Unlike Earth, the sun has no solid surface. About 3/4 of the sun's mass is hydrogen, and about 1/4 is helium. There are tiny amounts of other elements as well. The sun has an interior and an atmosphere. Interior includes the core, the radiation zone, or also known as the radiative zone, and the convection zone. So let's start with the core. The sun produces an enormous amount of energy in its core. The core is the central region. This energy is produced through nuclear fusion. In the process of nuclear fusion, hydrogen atoms join to form helium. Nuclear fusion requires extremely high temperatures and pressure, both of which are found in the core of the sun. The total mass of helium formed by nuclear fusion is slightly less than the mass of the hydrogen that goes into it. The remaining mass is energy. The radiation zone. The energy produced in the sun's core moves outward through the radiation zone. The radiation zone is a region of very tightly packed gas where energy moves mainly in the form of electromagnetic radiation. Because the radiation zone is so dense, energy can take more than 100,000 years to move through it. We can see the radiation zone or the radiative zone here. Finally, the convective zone. The convection zone is the outermost layer of the sun's interior. Hot gases rise from the bottom of the convection zone and gradually cool as they approach the top. Cooler gases sink, forming loops of gas that move energy toward the sun's surface. So looking at this picture, we want to see how is energy transferred from the core out through the sun. Energy through the radiative zone radiates outward until it comes in contact with the convective zone, where convection takes place. Remember, convection is that occurrence where warm materials are less dense, therefore they rise to the surface, or they rise higher. In this case, they're rising to the surface of the sun. Cooler materials, because they are more dense, sink back in to be rewarmed from the radiative zone, and that rewarmed material then transfers the energy back out to the surface again. Once at the surface, energy is simply released towards the Earth or the other planets in the solar system. So what is the structure of the sun? Let's specifically talk about the atmosphere of the sun. The sun has an atmosphere that stretches far into space. As you can see in this picture, the layers of the atmosphere become less dense the farther they are from the radiation zone. Like the sun's interior, the atmosphere is primarily composed of hydrogen and helium. The Sun's atmosphere includes the photosphere, the chromosphere, and the corona. Each layer has its own unique property. The photosphere. The photosphere is seen in this picture. It is considered the surface of the sun. You can see it in this area. The inner layer of the sun's atmosphere is called the photosphere. The sun does not have a solid surface, but the gases of the photosphere are thick enough to be visible. When you look at the image of the sun, you are looking at the photosphere. It is considered to be the sun's surface layer. Next is the chromosphere. At the start and at the end of a total eclipse, a reddish glow is visible just around the photosphere. This glow comes from the middle layer of the sun's atmosphere, the chromosphere. It comes from the Greek word chroma, which means color. So the chromosphere is the color sphere. And we can barely see it. It's actually in this picture going to be kind of the brighter yellow color right here. Finally, the corona. During a total solar eclipse, an even fainter layer of the sun becomes visible. As you can see in this picture, there is a faint layer of light surrounding the sun. This outer layer, which looks like a white or yellow halo around the sun, is called the corona, which means crown in Latin. The corona extends into space for millions of kilometers. It gradually thins into streams of electrically charged particles called the solar wind. And those solar winds may have been what affected Quebec and the power grid in 1989. So what features can you see on the sun? For hundreds of years, scientists have used special telescopes to study the sun. They have spotted a variety of features on the sun's surface. Features on or just above the sun's surface include sunspots, prominences, and solar flares. Sunspots. Photographs show dark areas on the sun's surface. These sunspots are areas of gas on the sun's surface that are cooler than the gases around them. In this picture, you can see the darker regions. Cooler gases don't give off as much light as hotter gases, which is why sunspots look dark. Sunspots look small, but in fact, they can be much larger than the Earth. The number of sunspots varies in a regular cycle, with the most sunspots appearing about once every 11 years. Prominences. Sunspots usually occur in groups. Huge loops of gas called prominences often link different parts of sunspot regions. So we can see a prominence in this picture. Solar flares. Sometimes the loops in sunspot regions suddenly connect, releasing large amounts of magnetic energy. The energy heats gas on the sun to millions of degrees Celsius, causing the gas to erupt into space. These eruptions are called solar flares. Solar wind. The solar wind is made up of electrical particles from the sun. Solar flares can greatly increase the solar wind, which means that more particles reach Earth's upper atmosphere. Earth's atmosphere and magnetic field normally block these particles. But near the north and south poles, the particles can enter Earth's atmosphere. There they create powerful electric currents that cause gas molecules in the atmosphere to glow. These particles cause the auroras near the poles. They can also cause magnetic storms like the one that we talked about in Quebec in 1989, causing a blackout.